Hi everyone, in this video we're going to be talking about complex numbers. Now when we're going to be talking about complex numbers, this is a very important number that we need to discuss first. It's the imaginary number I, or imaginary unit. If you've never seen this before, all I is the square root of -1. So by definition, anytime you see I and you know you're talking about the imaginary number, it equals square root -1. Now, where it officially comes from is this equation over here. It was asked, what number squared would give you -1? And the answer to that number is what we're calling I, this imaginary unit or number. Just an interesting side note, this number didn't exist in our vocabulary or numbering systems until about the 16th century. So I know that sounds like a long time ago, but it's relatively new if you think about numbers. Now, a complex number is of the form a plus bi. So a is a real number, b is also a real number, but I is what we just discussed, the imaginary number. And so we have numbers that are called complex numbers when they combine this combination here of a plus bi, a real number plus a number times an imaginary number. And we'll get into all of that. So in a complex number, if you break it apart, the a part, the part without the I, is called the real part, and then the part with the I is called the imaginary part. So you can separate the complex number into two parts, real plus imaginary. Some concepts involving complex numbers. So two complex numbers, a plus bi equals c plus di. They're equal, two complex numbers are equal if and only if their real parts are equal, and so are their imaginary parts. If a is 0 but b is not 0, then the complex number is considered purely imaginary, a pure imaginary number. Because if you think about it, if I have 0 real parts but 3 imaginary parts, all you're going to really see is the imaginary part. So we call that a pure imaginary number, when you only see something with the I. If a is not 0 and b is also not 0, then what you have is a complex number that's a non-real complex, and that's because it has a real part, but it also has this imaginary part, so it's not considered real because it's a combination of both real and imaginary. So we call that a non-real complex number. And then a complex number needs to be written in standard form most of the time. It's just a convention that we use. And so you always want to put the imaginary part last. So here's an example of it not in complex, in standard form. So the 4i is in the front and the real part's in the back. So you just want to switch the order. We're going to take -3 as our real part, write it first, and then positive 4i as the imaginary part and put it in the back. And that's considered standard form. And then you can put the I in front of the number b, or you can put it behind. A lot of times when we're dealing with radicals, which is going to come up in this video, we tend to put the I in front of the radical just to not make it confusing, to make you think maybe it's under the radical. So here's just an interesting image. Feel free to pause this and look at all the details here, but this is basically every number you've ever seen, including what we're learning today, complex numbers. And so officially, complex numbers are all the numbers, including the numbers you've dealt with for a very long time, the real numbers. So real numbers, inside of real numbers, look at this box here of real numbers. You have natural numbers. These are numbers that you would see like if you started counting, maybe trees outside, you would start with 1 and 2 and 3. So that's natural numbers. And then when you include 0, they're called whole numbers. So natural numbers plus 0 is whole numbers. And then when you start to include negatives, we call those integers. And then rational numbers are when you involve fractions. Fractions without decimals in them. So where the top number is an integer and the bottom number is an integer. And then irrational numbers are the numbers that can't be written with nice integer fractions. Very famous irrational number is the number pi. And then all of those are real numbers. But with real numbers, notice how you can write any real number. A real number is a plus bi, like we just talked about for complex numbers. But the b part, the imaginary part, is 0. So you don't even see it. You don't even see that there's an I part, an imaginary part. And so that's what we call real. And then if it's not real, it's non-real, a non-real complex. So in this case, you can have a couple of things. You can have a real part plus an imaginary part, and that's considered non-real complex. But you can also have just imaginary. So if the real part is missing, if it's 0, then all you're going to see is a term with I in it. So 3i, negative 2/3 I, and so on. And so these are considered purely imaginary because you don't have a real part, you only have imaginary. And these ones up here are examples of non-real complex, but everything on this screen is considered a complex number. Now what we're going to be doing is breaking down square roots of negative numbers, and now that we officially know what I is, we can use it to simplify these radicals. And so what you're going to have here is square root of a negative number, which used to be, doesn't exist, it's not real. Now we can actually talk about it. It's I times that square root of the positive number. So just a quick subtle thing to mention here. A is positive in this example. So the negative sign here is really like a -1. And so you can break this down. Square root of a negative number, you can take the negative and put it on 1. So you could say this is -1 times this positive number A. And then you can break apart this radical into the product of two radicals. And you're allowed to do this if not both numbers are negative. So let me say that one more time. As long as both numbers inside the radical are not negative when you're multiplying, you are allowed to separate the radical into two radicals when you're multiplying. So I'll emphasize this again when we do some examples. So you break this apart into a square root of -1, which is I, times square root A. And so that's how you're going to be rewriting your radicals of negative numbers from this point on. So let's try this out. Write the following as a product of a real number and I, using the definition we just talked about. So looking at letter A, up until now, you probably saw something like this and would say, well, that's not possible, that's not real. Well, that's true, it's not real, but we can still find it. And so square root of -16, you're going to break apart the negative sign and call that -1 inside the square root. So square root -1 times 16, and then the square root -1 part comes out and you call it I. So I was the square root of -1, which we addressed with this negative sign here. That became square root -1, which is I. And then square root 16, we know what it is. It's 4. So this is just 4i. So the shortcut is to just think about, well, what's square root of 16? I know it's 4. There's a negative, so that part's going to turn into the I. So that's the fast way to do it. Let's try the next one, part B. Square root -70. Well, the -1, that square root of -1 is written as I, and then we just have square root of 70, which doesn't break down, so we leave it like that. And then the last one here, we take apart the square root -1, we take it out and we call that I, and then square root 48, just like part B, we would leave this answer if we couldn't break down 48, but we can. So I want to go into this one, this example, in a little bit more detail because this is going to help you in future problems that you have to solve. So anytime you have a radical and you think maybe you can break this down, meaning there's like a perfect square in it because this is a square root, what I would recommend if you don't see it just by looking is make a list. So make a list of the factors of that number, of this radicand. So 48, you can break it down as 1 times 48, 2 times 24, 3 times 16, 4 times 12, and 8 times 6. And so what you want to do is you want to look at this list of factors and think about, well, what number do I know the square root of on this list? And 16 is a perfect square. So 4 is also a perfect square, but you always want to pick the biggest one on your list. So 16 and 3 are the same thing as 48. So you can say square root 48 is the same as square root 16 times 3. And then you can take the square root of 16. And so square root 16 is 4. The I was already out front from the -1. Square root -1 became the I part. And then the 3, we can't break that down any further, so it stays inside the radical. So square root -48 is exactly the same as 4i square root 3. Now that we've broken down some radicals involving negative numbers, let's solve some actual equations. So, part A, what number squared equals -9? well, before today, no real number did that. We would say doesn't exist, there's no real number. But that's, even though that's still true, the number's imaginary, so we are going to go forward and solve. So you're going to square root both sides of this equation. And remember, anytime you physically find yourself taking a square root, like there was no square root in the problem to begin with, but you take the square root, you write it on your paper, then you want to put the plus and minus, because technically when you squared it to get back to x squared, it could have been negative or positive to begin with. So don't forget your plus and minus. Now, before I put it, see if you can do the next step. You have a square root of a negative number. So you're going to take out the square root negative 1, and that's going to be called the I part. Okay? And then what's left is just square root positive 9, which we know is 3. So final answer, plus and minus 3i. And you can write them separately as a solution set of negative 3i, comma 3i. So there's two answers there. And if you take it and you want to check, you can take negative 3i and square it, plug it right back in here and square it, and you're going to get negative 9. Same thing with 3i. And then, because remember what we talked about at the very beginning of this video, I squared is negative 1. So the negative 3 squared is 9, but then I squared is negative 1. So when you square that, you are going to get a negative 9. So let's try part B. You're going to solve for x again, but this time you have to do one step in the beginning. You need to subtract 24. So x squared is negative 24, and then you square root both sides of this equation. Don't forget your plus and minus. And then you have a negative inside your square root, so you're going to say square root negative 1 is I, and then you're going to leave the 24 inside the radical. And then this would be the answer if you couldn't break down 24. So you think about, well, how can I possibly break down 24? Is there any perfect squares that make up 24? And there is. It's a 4 times 6. So if you break apart 24 is 4 times 6, we know the square root of 4. So that's going to come out. We call that 2i. So the I was out. Square root 4 became 2. And then 6 doesn't break down. We don't know the square root of 6. It's not a nice number. So we leave that in the radical. And so our solution set is negative 2i square root 6. And then also positive 2i square root 6. And again, you can always check. You can take these answers one at a time and plug them back into your equation, square them, add 24, and you will get 0. Okay, so I mentioned this before, and then I just want to go into more detail about it. So when you're working with negative radicands, so that means the value inside the radical sign, we're going to use the definition that square root negative a equals I times square root positive a before any other operations or rules for radicals. So you have to do this first, because if you don't, it's going to lead to the wrong answer, and I'll show you why. So it's because mostly of this rule here. So if you take a square root times a square root, then notice they're separated, two square roots being multiplied. You can put them together only if and only if they're not both negative to begin with. So you have to be careful here now that we're dealing with negative numbers. So if you've dealt with square roots in the past, you could freely use this fact here. You can start with their product inside a square root, and you can separate it into two separate square roots. Or you can start with two separate square roots and put them together like this if they're being multiplied. But now you have to be careful because of the I part, the imaginary part. So here's why. Here's an example. So if you look at what we start with, square root of negative 4 times negative 9. Inside the radical, notice these are both negative numbers, so if I multiply them, I get positive 36, all still inside the radical. Square root of 36, we know, is 6. Okay, let's go the other way now. Let's start with two separate radicals with both negative radicands. So square root negative 4, square root negative 9. Well, from what we've been talking about so far in the video, we know that the first square root here, this is going to have an I in it because it's negative, and then square root of 4 is 2. So that's 2i. This second radical is going to have an I in it because of the negative 1, and then square root of 9 is 3. So that's 3i. And so you multiply 2 times 3 to get 6. I times I is I squared, and we talked about that I squared is negative 1. So 6 times negative 1 is negative 6. And so notice we got two different answers depending on how we did this problem. When the two factors started in the same radical, we got positive 6. when the two factors started in two separate radicals? We got -6. Therefore, these are not equal. You can't separate them. You can't separate a product of two negative numbers inside the square root into two separate square roots, or vice versa. And so that's what I'm saying right back here. You're going to use this definition first. You're going to pull out I first, and we'll do it in another example so you see what I mean. So let's multiply or divide as indicated and simplify each answer. So letter A says square root -7 times square root -7. Notice both radicands, both values in the radical are negative. So this is what I was just talking about. So you have to rewrite with I first. This must be done first, and if you get into this habit of doing this first, then you'll be fine. You're going to get the right answer if you do it first. So the very first thing you do is you say, well, square root -1 times 7, so the square root -1 is I, and you do that for both radicals. The i's come out, the square root 7 stays, and then you can combine the terms. You can say I times I is I squared. Square root 7 times itself is square root 7 squared, and then I squared we know is -1. Square root of 7, square root 7 squared, excuse me, is just 7. So final answer is just -7. All right, if that makes sense to you, try to pause this and do letter B before I show you. Okay, so we're going to pull out the I from the -1s. So we're going to say -1 inside the square root is represented by I. We're going to do that for both radicals. So it's I times square root +6 times I times square root +10. Then we get I times I, which is I squared. These are both positive radicands, so we can go ahead and put those together. So that this is allowed. They're not both negative numbers, so we can put them together. We can say square root 6 times square root 10 can be combined to make square root 60. Now, square root 6 we didn't know, and square root 10 we didn't know. We can't simplify either one of those, but when we combine them and make 60, we can simplify square root 60. There is a perfect square that makes up 60, and it's 4. So 4 and 15 is the best way for you to break down 60, because we know the square root of 4. So we're going to start replacing. We know I squared is -1. We know square root of 4 is 2. And then square root 15 we don't know, so we're just going to leave it inside the square root. So then there's 2I squared, square root 15, and then that I squared we talked about was -1. So final answer, -2 times square root 15. And you can check on your calculator too if you want to make sure. You can type the final answer in, see what it equals as a decimal, and then type in this individual, these two individual radicals being multiplied, and then see if the decimals match, and they will. On letter C, we're dividing. So this one, similar process, but division, we're going to have to think about it just a tiny bit differently. So we are still going to work with I first. So don't forget, you're always going to pull out the -1, the square root -1 first. So that's I on top, I on bottom, and then positive radicands after that. So square root 20 over square root 2. And so now that these are both positive radicands, you can combine them. So just like we did with these two positive radicands back here, we multiplied. So you're just going to divide them. So you're going to say square root 20 divided by square root 2 is just square root 10. And then the i's divided out. So that's why they're gone. So the final answer here is square root 10. So our last one here, letter D, only the numerator is going to have an I in it, because notice the denominator isn't negative. There's no negative radical here. So in the numerator, we have square root -1 times 48, and so we get I times positive square root 48. And then you can combine these two radicals by dividing. So you can say square root 48 divided by 24, and you get I square root 2. Next example, we're going to write this expression in standard form a plus bi. Okay, so let me just tell you why we're doing this. This is going to be useful when we start solving equations using the quadratic formula. So this is a typical answer you're going to get when you use a quadratic formula, but you need to write it in standard form. So we're going to work all the way to simplify this down and then write the imaginary and real parts separate from each other. So let's start with figuring out, well, what is this radical actually going to look like with an I in it? So square root -1, we rewrite that part as I, and we're left with positive square root 128. And so now this is the part where you're going to break down 128, and you're going to say, okay, well, how can I break apart 128 to where there's a perfect square in it? And so if it's not easy to figure out, I would make a list. So 128 is 1 times 128, or 2 times 64, or 4 times 32, or 8 times 16. And then you look at your list and you look for perfect squares, numbers you know the square root of. And there's 2 of them. Well, actually there's 3. I should have circled the middle one. 4 is also a perfect square. But 64 is a perfect square. 16 is a perfect square. So is 4. There's a lot of perfect squares on this list. But like I said earlier, you're going to pick the biggest one. So pick the largest perfect square, and you're going to use that to break down your radical. So square root 128 is the same as square root 64 times 2. And then we know the square root of 64 is 8. And so the 8 is also now outside the radical with I. And then square root 2 stays here. And then this would be the answer if you couldn't simplify further. You would just separate the real from imaginary. But we can simplify further. If you notice, that both terms on top have an 8. The bottom has a 4, so we can factor. So we're going to factor out a 4 from the top, and then divide out the 4 on bottom with the 4 on top. And so now we have -2 is the real part, plus 2i square root 2 as the imaginary part. So this is now standard form. Standard form basically just says, write your real part first and separate from the imaginary part, which you write second. And the I, like I said at the very beginning, you can put the I in front of the radical or in the back. It's just usually habit to write the I in front of the radical, just so you don't accidentally think it's underneath the radical sign. So it's just a good habit to put it right in front. Now we're going to add and subtract complex numbers. So we officially know about the complex numbers. We know how to figure out the square root of a negative number now. So now we're going to start adding and subtracting. And then you can probably guess what's after that. Multiplying and dividing will come after. So to add and subtract complex numbers, it's really, really nice. All you're going to do is you're going to take the real parts, in this case A and C, and add them. And then separately, the imaginary parts, BI plus DI, and add them. And the same exact thing happens with subtraction. You subtract the real parts, and you subtract the imaginary parts. So really straightforward. So let's practice adding and subtracting complex numbers. So you have 3 minus 4i, that's one complex number, plus -2 plus 6i, another complex number. So like we just talked about, combine the real parts, and then separately, combine the imaginary parts. So the real parts, you get 3 plus -2, and then imaginary, you have -4 plus 6, and those are both going to be with I. And so when you simplify, you just get 1 for the real part, plus 2i for the imaginary part, and that's the answer. So if it makes sense, pause the video and try part B before I show you. Okay, so on part B, same thing we've been doing, combining real with real, imaginary with imaginary. So you're going to combine -6 with -4 with -6, and then you're going to combine 3 with -7. But be careful, you're subtracting this time, so it's 3 minus -7. So you're actually going to add those ones. And so we end up having -10 for the real part plus positive 10i for the imaginary part. All right, I mentioned it was coming, so we just did addition and subtraction. Now we're ready for multiplication. Multiplication of complex numbers, very much the same as multiplication you've done up until this point. Basically, it's going to be foiling. And then you just have to remember one thing. You have to remember that I squared equals -1. And I'll show you when it comes up in the next example. Now, this is the formula for multiplying complex numbers. You do not have to memorize it, and I'll explain why. It's because this formula, this is just foiling. So this is just what you're going to get after you foil. And you'll see in our example. And foil or the box method. So let's find each product. So notice you are going to have to foil or use the box method for working out this product. It's a binomial times another binomial. Okay? And so if you think you got it, go ahead and pause and try to FOIL this out. All right, so here's what we get, and I'll just walk through the FOILing process. So first times first term times first term, and then next is going to be outer times outer, so outer term times the outer term, and then inner times inner, and then last times last. Okay, so it's just a FOIL process. So there's no formula you have to memorize. It's just FOIL out this product and then start simplifying. Okay, so when you simplify, you're going to end up with 6 plus 8i minus 9i. And then in the last term here, because they both had an I in it, you multiply negative 3 times 4. That's why we have a negative 12. But then I times I. So that's the I squared part I was mentioning. Now you're going to combine like terms, and the like terms are here in the middle. They both have I in it, single I. So that's going to give you minus 1i in the middle. 8i minus 9i is just negative 1i. And then wherever you have an I squared, this is what I was mentioning, I squared is negative 1. So this is negative 12 times negative 1. Be careful, don't subtract 1. It's not negative 12 minus 1. It's negative 12 times I squared, so negative 12 times negative 1. So I would really recommend using parentheses when you substitute I squared for negative 1. If you don't use the parentheses, you might accidentally think you're subtracting 12 minus 1. So use parentheses. I squared is negative 1, so parentheses where I squared used to be. And then simplify. This becomes positive 12, so you add that to the real part, so 18, and then minus 1i. On part B here, we're still going to FOIL this out, but notice it's just the same binomial times itself because it's squared. So it's 4 plus 3i times 4 plus 3i. So if you think you want to try this out, go ahead and pause and try it, and then I'll show you. Okay, so if you did the FOILing, because it's the same binomial squared, you end up with 2 of the same term in the middle. So I just wrote it as twice 4 times 3i. And then in the back, it was just 3i times itself. And then the front, it was just 4 times 4. Okay, so we start simplifying. And the last term, again, has an I squared in it. So I'm going to replace I squared with what it equals, negative 1. And it's 9 times negative 1. And so that's now a real number. So this is negative 9. And you're going to combine it with the real number 16. And you get 7 plus 24i. Final answer. Okay, let's try one more here. And now this is 6 plus 5i times 6 minus 5i. Now I picked this one for a reason. You're going to find why in just a moment. Again, pause it if you'd like to work it out yourself, and then I'll show you how. Okay, so when you start the FOIL process, you have 6 times 6, and then the outer is 6 times negative 5i. The inner is 5i times positive 6. And then last is negative 5i times itself. And so look at what happens in the middle 2 terms. The 2 terms in the middle of your multiplying process. If you use the box method or if you use FOIL, the 2 terms in the middle, what does that add up to? 0. Okay, those terms are gone. The 2 terms in the middle, whenever you multiply like this, and I'll explain it in just a moment, they're going to add up to 0. Okay, so here's what I'm talking about. Whenever you're multiplying a binomial times the same binomial, but the sign in the middle switched. So notice this was a plus, and this one was a minus, but other than that, everything was the same. Whenever you do that, the 2 terms in the middle will add up to 0. And so what this is called is a complex conjugate. And so if I have 6 plus 5i, the complex conjugate of that is 6 minus 5i. And vice versa. If I had 6 minus 5i first, its complex conjugate is 6 plus 5i. So when the sign on the imaginary term changes, that's a conjugate of what you had previously. And so again, every time you do that, multiply a binomial times its conjugate, or a complex number like this times its conjugate, it's going to give you a 0 for the 2 terms in the middle. So that's a nice check to make sure you FOILed right. If the 2 terms in the middle didn't add up to 0, but you were multiplying a number times its conjugate, then check your work because it should be 0. So then we keep simplifying. We get 36 times negative 25i squared, and then we know that I squared is negative 1, and so this is now a positive 25, so we just have 61 as our answer. Or if you want to write it in complex standard form, you can say 61 for the real part plus nothing or 0 for the imaginary part. Alright, so we were just talking about, and we saw an example with complex conjugates, so let's talk about it a little bit more. A plus bi is our complex number, and its conjugate is a minus bi, or vice versa. So if I start with the minus sign, the conjugate would be if I put in the plus sign. And so we just saw an example of it, but you can kind of skip some steps on your foiling because of what I mentioned. The two terms in the middle of the multiplication or FOIL process will go away, and so you won't have anything in the middle here. They'll add up to 0. So you can kind of skip that if you know that that's what you're working with, and you can say a squared plus b squared is this result. But only when you're dealing with complex conjugates. So be careful. If it's not complex conjugates, then don't skip anything. Just FOIL it the regular way. Alright, so this is going to be dividing. So far, just to recap, we've added, subtracted, and multiplied with complex numbers. So now we're going to divide, and this one's a little different, so I want to make sure you see that we're doing something different now. It says write this quotient, which just is the answer to division, in standard form. And so you might think maybe I should try long division or something like that, but here's the trick. You actually multiply. So even though we're dividing, and even though we're told to write this quotient a certain way, the rule or the trick is really to multiply. And you multiply by the complex conjugate of the denominator. So anytime you see a quotient like this with complex numbers, where you see like I in it, take the bottom, in this case 5 minus I, and find its conjugate. So change that minus to a plus sign. Whatever sign you have in the middle, just put it the opposite. So it was a minus, so now it's plus. And then you're going to multiply top and bottom by that complex conjugate. So that's the process for dividing. I know it seems a little strange, but let me just clarify one more time. When you're told to find the quotient or to divide with complex numbers, you actually multiply. You multiply by this complex conjugate over itself. Okay, so remember, this is just the funny looking number 1 anytime you multiply by something over itself. And so this is just the number 1 right here. And then we're going to FOIL this out. So try it, pause this, and FOIL the top, FOIL the bottom, and then check what you got in just a moment. Okay, so here's what we get after we FOIL out the top and bottom. The denominator, we could take the shortcut if you want, or you can do it the full FOIL process, and then you'll see that the two terms in the middle added up to 0. The numerator, you have to just FOIL or use the box. You have to do all 4 terms. So you multiplied the numerator, both binomials up here, multiplied the denominator, and then after all that, you just start simplifying, combining any like terms, replacing I squared with negative 1. Okay, so on top, 3i plus 10i, that's where 13i came from. And notice why there's a 13 here for the real part. You had 15 real parts, but then 2 times I squared. So this is 2 times negative 1. So this is really a minus 2 right here. So that's why there's 13. 15 minus 2. And then on bottom, why did I get 26? Think about that. Okay, it's just because the same thing, I squared is negative 1. So this is 25 minus negative 1, or 25 plus 1. So that's why the bottom was 26. Now, after all of that, you would think, okay, let me box in my answer, but in standard form, you have to separate the real part from the imaginary part. And in this one, we also can factor. So let's factor out a 13 from the top, because 13 actually goes into 26. So we're going to divide top and bottom by 13. And so we end up with 1 plus 1i over 2. But I can't box this in either, again, because I need to separate the real part from the imaginary part. So my final answer is 1/2 as the real part plus 1/2 I for the imaginary part. So this would be considered the answer in lowest terms and also in standard form. Let's try this next one. Write the quotient in standard form. All right, so in the last example, we had a quotient in if you remember, we multiplied by the conjugate of the denominator. So now think about it. Well, what's the conjugate of this denominator? I just have I. Well, you just change the sign in front of I, and that's going to give you the conjugate. So you're going to multiply top and bottom by negative I. So if you think about it, this is really like saying 0 plus I. So the conjugate is 0 minus I. And so you're going to multiply top and bottom by the complex conjugate of the denominator. And so this one's really nice. You don't have to FOIL anything out. We just have negative 3I on top, negative I times I, or I squared on bottom. And then we know I squared is negative 1. So this negative that was in front of I squared turned the negative 1 into positive 1. And that's our final answer. Negative 3I, or if you want to put the real part on, this is 0 minus 3I. Now you're going to be able to solve quadratic equations where the answers are complex. So you've probably came across this in the past when you dealt with quadratic equations, but if you ever had a negative inside your radical, you might have said something like the answer is just non-real. But we're going to go further now that we know how to work with radicals of negative numbers. Okay, so remembering how to solve a quadratic equation, we're going to end up using the quadratic formula on this one. So recall, whenever you're dealing with a quadratic equation, you want it to equal 0. That way you can either factor it or you can use the quadratic formula. In this case, it doesn't factor well, so we're going to use the quadratic formula, where a is 9, b is negative 6, and c is 5. So I'm going to show you what the formula is in case you forgot. So here's your quadratic formula, and we're just going to replace all of our letters with the numbers from our equation. Okay, so we have all of our values in place in our quadratic formula, and then we're just going to start simplifying. So when you simplify the radical here, this becomes 36, and then minus, I'll calculate it really fast, 4 times 9 times 5, minus 180, and that's total of negative 144. So in the past you might have said something like, okay, here's my answer, but this is non-real. But now we're going to go further, and we're going to say, okay, square root negative 144 is going to have an I in it, and then we deal with square root 144. Okay, so hopefully this part makes sense. Square root negative 1 was represented by I, and square root positive 144 we know is 12. And so we can't stop here, even though this looks pretty nice. We still have to simplify and separate real parts from imaginary parts. So notice all three terms in this expression have a factor of 6. So we just divide 6 by 6, we got 1. 12 by 6 is 2, and then the bottom 18 by 6 was 3. And then your final answer, you just want to separate the 1/3 from the 2/3 I. So this would be the final answer. And then you can separate it as two separate answers if you'd like, as a solution set. So you can say 1/3 plus 2/3 I, and then your other answer is 1/3 minus 2/3 I. The last thing we want to mention for complex numbers is something interesting, and it has to do with the powers of the number I. And so why this is interesting is because you'll see this pattern. So I to the first power is just itself. I squared we talked about a lot. It's negative 1. But now let's go further. I to the third is negative I. Okay, well, why is that? And I'll show you why. I to the fourth is just 1. Okay, interesting. And then I to the fifth is I again. Well, I to the first was also I. I to the sixth is negative 1 again. Oh, well, so is I squared. I to the seventh is negative I. Wait, so is I to the third. And so on. This repeats. This pattern just repeats. I to the ninth would be the same as I to the first. I to the 10th would be the same as I squared. And so on and so on and so on. So every single power of I that you will ever come across is one of these four answers. I, negative 1, negative I, or 1. So your answers are either plus and minus 1 or plus and minus I every single time. Now you don't have to know how we got these, but I do just want to show them to you. So let's break a couple of them down. We knew the first two. So I to the third is just the same thing as I squared times I, and this is from your rules of exponents. I squared times I to the 1, you just add them up, that's I cubed, I to the third. But we knew I squared was -1, and I is just itself, so the answer is -I. So that's why that answer is -I. Let's look at the next one, I to the 4th. I to the 4th, you can break apart using your rules of exponents as I squared times I squared. If you add 2 plus 2, you get this exponent of 4. Well, we know I squared is -1, so this is just -1 times -1, which is 1. Okay, let's do I to the 5th. Let's see why it's I again. So I to the 5th. Well, you can break apart I to the 5th as I to the 4th times I. And I to the 4th is so nice, it's just 1. And so it's just 1 times I, which is I. And let's do one more. Let's do I to the 6th. So I to the 6th is just I to the 4th times I squared. If you add the exponents, 4 plus 2, you get 6. And then I to the 4th is that nice number 1. And so I squared, we've talked about a lot, is -1. So this is just 1 times -1. Final answer, -1. So this was just a quick proof on why these are going to be what they are, and then they're just going to keep repeating over and over again. And they keep repeating because of this I to the 4th. You can basically write everything in terms of I to the 4th, and then whatever's left over to get you to your actual power. And I'll explain that with the next example. Alright, so our last example, we're going to be simplifying powers of I. Let's start with letter A. So the best way to do this is to write things in terms of I to the 4th because it's so nice. It's just the number 1. So I to the 15th, what you're going to do, and this number's not so bad. You can probably just kind of guess or come up with this, but I'm going to explain. You want to just divide by 4. So 15 is not that hard to deal with, but maybe if it was like letter C, 1,500, 1,500, that's a lot larger number. So divide your power by 4, and then notice what you get. The answer is 3, remainder 3. 4 goes into 15 evenly 3 times, but then there's 3 left over. Okay, if you want to think of it, it's 12. 4 times 3 is 12, and then 13, 14, 15, 3 more will get you to 15. Now, why I wanted to do that, here's why. Now, if I know how many times 4 goes into 15, I can break this apart. I can say, okay, I to the 4th 3 times gets me close to 15. That's 12 of them, actually, 12 powers. And then I have a remainder of 3. And so this is super nice because I to the 4th is 1. So this is just 1 to the 3rd power. So I want to know how many times 4 goes into my power, and then I can rewrite what I have as I to the 4th that many times. Okay? But then I to the 3rd, that was on our list. So if you remembered what I to the 3rd equaled, you can just put that here. But if you didn't remember, you can break it apart. Okay, so this is what I'm saying. If you remembered I to the 3rd from our list was -I, you can just replace it. But if you ever forget, you can just say, well, I to the 3rd is I squared times I. You can always write things in terms of the values of I you know about. We know what I is, it's just I. We know what I squared is, it's -1. So this is just -1 times I. So if you ever forget, you can just break it down like I did here. And so this is just 1 times -I. Final answer, -I. And so any power of I, in this case I to the 15th power, is the same as either, this is what I said on the last slide, plus and minus 1 or plus and minus I. So this is just equal to -I. Let's try letter B. Letter B is a little interesting. Okay, letter B is a little different. It's a negative exponent, so what we're going to do here is actually multiply by 1. Okay, remember you're always allowed to multiply anything by 1 to help you out. And in this case, it's going to help us out because that's a power of I. So this is kind of the tricky part. You have to know to multiply by the number 1. And then we know the number 1 is I to the 4th. So I to the 4th is the same thing as 1. And then we have a rule of exponents that says if I'm multiplying the same base, I add my exponents. And so this is just I to the -3 plus 4, which is I to the 1, which is I. So I to the -3 power is the same as just regular I. And our last one, part C, I to the 1500. So I to 1,500th power. So this is where we're going to go back and divide by 4 again. So how many times is 1,500 divide by 4 evenly? And it's actually even. It goes in nice 375 times. So there's no remainder. Last time there was a remainder, and so like back here we had a remainder 3, and so that was this part that we multiplied by, this I3rd here. So this time, because there's no remainder, we just break this apart as I to the 4th to the 375th power, because 4 times 375 is 1,500. And then I to the 4th we know is 1, and 1 to any power is just 1. So I to the 1,500 is just 1. And that's it.